SAS demonstration video, Simple Descriptive Statistics. The dataset used for this demonstration is called TOMHS, T-O-M-H-S, which stands for Treatment of Mild Hypertension Study. This randomized, controlled, double-blind trial was conducted at 4 clinical sites in the U.S. between 1986 and February 1992. The study compared the combined effects of diet treatment and one of 5 active drug regimens with diet treatment alone for the 4-year management of 902 middle-aged adults with mild hypertension, defined as diastolic blood pressure between 85 and 99. There were 127 variables collected. We are going to use 8 variables for this demonstration. The dataset TOMHS, or TOMHS.txt, has 100 observations, which was a random sample of the 902 participants in the study. The raw data is in column format, and we are using pointers and informats to read the data into SAS and create a SAS dataset called weight. Notice that I have created formats for gender and ever smoke, and labels for the variables BL, which equals baseline cholesterol, and ever smoke, which equals ever smoke cigarettes. So the variables that are being read in, at column 1 we have PTID for patient ID. At column 12 we're reading in clinic. Both of these are character variables. At column 27 we're reading in age. Column 30 we're reading in gender. And all the way out to column 140 where we're reading in baseline cholesterol. So we're reading in selected variables at different columns. Notice again that we're using informats. So for example, the informat for age is 2 dot, which means that age is a number that's 2 digits wide and there are no values to the right of the decimal point. So the first thing we're going to do is print out our data. So we're just going to have a PROC print and a run statement, and we have a title statement. And so with the PROC print and the run statement, we are going to be printing out all the variables in our data set, and they will appear as the variables were input into the SAS data set. So let's run this code. And here we have a printout of the 5 observations from the TOMHS study. And notice that we had a label statement in our PROC print so that the headings of the columns are the actual variable labels, ever smoke cigarettes, baseline cholesterol, and these are the variables in the order that they were read into SAS. If we look at the log, we see that there were 5 observations read from the dataset work.weight for the procedure print, and that 100 records were read from the actual dataset. Let's say we only wanted to print out selected variables. We would do this with a var statement. And I know we've done this before, but again, I'm trying to reinforce the concepts that we've been using in the earlier weeks of the class. So here we're going to just print out the variables height, weight, and BMI. So these are just selected variables of the first 5 observations. Notice here that SAS automatically produces this column OBS, which lists those 5 observations. If we didn't want SAS to print out that column, we could add an option to the print procedure called No OBS. The No OBS option takes out that column of observation number from the output. So here you see we have the same printout except that the column OBS has been left out. And that's nice if you're producing output that you want to show to somebody to not have that observation column. Now let's take a look at the PROC means procedure. So here we're interested in doing PROC means on the numeric variables height, weight, and BMI. And we're going to just get the default statistics for PROC means because we haven't specified any statistics in our PROC statement. So if we run this code, we see that for the 3 variables, height, weight, and BMI, that all of the variables have 100 non-missing observations, which means that all 100 observations in our data set had a height recorded and a weight recorded, and so therefore when I calculated BMI, I have the full data set has values of BMI recorded for each observation. And by default, the means procedure prints out the mean, the standard deviation, the minimum, and the maximum. Notice that by default, SAS prints out a large number of digits to the right of the decimal point, and that's not that attractive. So it might be nice if we could have SAS printed out so that maybe only 2 digits are printed to the right of the decimal point. So in this next procedure, we are going to, first of all, we're going to specify certain statistics in the PROC statement, and we're going to also request that SAS only print out 2 digits to the right of the decimal point. So here we're specifying the mean, the median, the standard deviation, minimum, maximum, and we're telling SAS to only print out 2 digits to the right of the decimal point, or max dec equals 2. So let's see how the output changes when we run this procedure. So here, notice now the output is a lot nicer to look at because we only have 2 values to the right of the decimal point. And it shows the mean, the median, standard deviation, minimum, and maximum. We can also get our statistics separately for each clinical center. And also what I'm requesting is an option that limits the width of the columns of output displayed. So here the FW option is telling SAS to make the column width 8. Again, we're requesting that max dec equals 2. And the way we are able to get statistics separately for each clinical center is with a class statement. So in the class statement, we put our categorical variable clinic, and then we're listing the 3 variables height, weight, and BMI. So let's look at how the output looks with our class statement. So here we see that now we have our statistics by clinic. And again, it gives for each clinic, first of all, it tells the number of observations in the data set. And so let's say that we had 18 observations, but not everybody in Clinic A had height and weight recorded. The N-obs would tell the total observations that were in Clinic A, and the N would give the number of non-missing. In this situation, all 18 of these subjects from Clinic A had height and weight recorded. So that's why these numbers match up. And again, we have our mean, our standard deviation, minimum, and maximum. Another way of getting descriptive statistics by clinic is by using a sort and by statement. So here we have PROC sort by clinic run. So we're sorting our data set by clinic, and then we are going to run the procedure PROC means, and we have a by clinic in the procedure which tells SAS to show the output by clinic. Basically, any procedure in SAS can display data with a by group as long as you have a PROC sort and a by statement. So any of the procedures, PROC FREQ, PROC means, PROC print, if we do a PROC sort like we are here doing PROC sort by clinic, and then we have the by clinic within the procedure, the output will be displayed by that particular categorical variable. The other thing that I'm doing in this PROC means is I'm also including CLM for 95% confidence limits. So we are requesting the 95% confidence limits for height, weight, and BMI within clinic. So let's see how the output looks when we sort the data by clinic. So notice here that in this example, we have Clinic A, and it shows height, weight, BMI, and it also provides us with the lower and upper 95% confidence limit. And so it looks slightly different than the previous example where we had a class statement. Again, the statistics are shown by clinic, but here in the class statement you see it in one table, and here you see the output for each group. Clinic equals A, clinic equals B, clinic equals C, and clinic equals D. Let's say you wanted a 99% confidence limit for the mean using the alpha option. So here, if we want a 99% confidence limit, we have our CLM option, and then we say alpha equals 0.01 to get a 99% confidence interval. So here we are. We now have a lower 99% confidence limit and an upper 99% confidence limit. And in this example, we didn't have a by statement, we didn't have a class statement, so it's going to give us all the patients together. Now let's turn to PROC FREQ. So to get a simple one-way table of gender and clinic, we just have the table statement. And again, this is something we've already been doing. And here, because I had a format statement that was in my data step, it lists gender, males, and females. And here it is, the observations from each of the clinics. Once again, we have complete data. Every observation has a code for gender, and every observation has a code for what clinic that particular participant was involved with. Let's say we did not want to show the cumulative percentages. So we can add the option no cum, which deletes the cumulative percentages from the output. So let's run this bit of code, and we see here that all we're shown is the frequency and the percent, no cumulative percentages. Above you see that we are automatically by default given the cumulative frequency and the cumulative percent. I also want to point out that any time that you're adding options in PROC FREQ, like no cum, you do it after the slash. So you'll have the table statement and a slash and then some options. Now let's say we wanted to do a two-way table of gender and clinic. So we're going to request a two-way table by putting an asterisk between the two variables that we want the cross-tabulation of. So here we're doing a cross-tabulation table of gender and clinic. And let's take a look at what is automatically given by default. Okay, so how do we interpret the frequency, the percent, the row percent, and column percent? So let's take a look at males from clinic A. So the first number, 12, represents the actual number of participants. These are the actual number of male participants from clinic A. There are 12 male participants. The second number is the percentage. So there are 12% of all participants are males from clinic A. So this is the percent of the total. The third number is the row percent. So there's approximately 16% of males are from clinic A. So we have 73 males altogether, 12 of them are from clinic A, so about 16%. And then finally, we have the column percent. 67 participants from clinic A are males. So there are 18 participants from clinic A, 12 of them are males, about 67%. Let's say we don't want all these numbers. Let's say all we're interested in is the actual count. So we can add the options no row, no col, no percent. And then all we will see in our frequency table is going to be just the counts of gender and clinic. So notice here in this output, all we see are the actual number of males and females who participated at each clinic. There are no percentages. And this was done by putting in the no row, no col, and no percent option. Another way that you can request your data to appear in the output from PROC FREQ is with a list option. And this will give you what we call list style output. So I've added this list option, and you see here our data is in list format, and we have the cumulative frequency and cumulative percent. So it almost looks like a one-way frequency table. This is a form of PROC FREQ that I don't use. So I don't use the list option very frequently, but I wanted to show you that it is an option that exists with SAS. Let's say we wanted to do multiple tables. So we wanted to do a table of gender by clinic and also gender by ever smoke. So to do that, we can do sex, star, and then in parentheses list all the other variables that we want cross-tabulation tables for. So let's see what happens here. And we see here now that there are two tables automatically produced, sex and clinic, and sex and ever smoke cigarettes. And notice that the label for ever smoke cigarettes is printed out in the output. How could we use PROC FREQ to get the distribution of gender by smoking status within clinic? So to get SAS to do that, we would write PROC FREQ tables clinic star sex star ever smoke. This will give us tables that show us the distribution of gender by smoking status within clinic. So let's see what happens if we run this. And here we are going to see four separate tables. Clinic A, gender by ever smoke. Clinic B, gender by ever smoke. Clinic C, gender by ever smoke. And Clinic D, gender by ever smoke. The other way we could do this is with a PROC sort. So we could go PROC sort by clinic, and then we could go PROC FREQ tables sex star ever smoke by clinic. So again, as I was saying to you earlier, we can use the PROC sort and the by statement with any procedure. So let's run this and see what happens. And here you see we have clinic equals A, clinic equals B, clinic equals C, clinic equals D. So there are two ways that we could get the distribution of gender by smoking status within clinic. The last procedure I want to talk about in this demonstration is PROC Univariate. PROC Univariate generates a lot of output. So let's take a look at doing PROC Univariate for the variable BMI. So here we're not asking for any options. We're just doing PROC Univariate, listing the variable, and seeing what we get. The first part of the output gives us all sorts of the number, the mean, standard deviation, the sum of the observations, so it adds up BMI across all 100 observations. It gives us basic statistical measures, the mean, the median, the mode, standard deviation, variance, range, interquartile range. It also gives tests for location. So it's giving us a one sample test that's testing whether BMI differs from a population value of 0. And not surprisingly, we have a highly significant p-value, which means that the true mean BMI of the population of individuals with mild hypertension differs from a mu of 0, which is expected. We wouldn't expect that this population has a BMI of 0. And so these are the different tests: the student's t-test, the non-parametric test, the sign test, and the sign rank test are all automatically given in PROC Univariate. And then it shows the quantiles. So it gives you the 50th percentile, the median, the 25th, the 75th, and it tells you the extreme observations. What were the lowest values, the 5 lowest values in your data set? What were the 5 highest values in the data set? Let's say that we wanted to test whether the BMI of this group of hypertensive individuals differs from the population BMI of, say, 25. So we want to actually make this one sample test a little more realistic. So here we're going to change the option to mu equals 25. By default, it tests for the value of 0. So in this example, we're going to show whether the one sample t-test with the null hypothesis of BMI equals 25 gives us any different results. So here again we get all the output that we did before, but notice the test for location, we have mu equals 25. In the previous output, the test for location was for mu equals 0. And so here, once again, the conclusion would be that the true mean BMI of the population of individuals with mild hypertension differs from a mu equal to 25. So this group with their mean BMI of around 29 differs from a population where the mean is 25. Another thing that can be very helpful with PROC Univariate is to have an ID statement. And what the ID statement does is it will actually list the ID along with the 5 lowest and highest values. So this is very helpful if you're trying to determine whether there are errors or outliers in your data set that need further investigation. So if I am doing work for a researcher and we are concerned that there may have been a data entry error and we want to figure out which patients had the data entry error, I would include an ID statement with PROC Univariate. So here you see that for our extreme observations, not only does it list the 5 highest and 5 lowest, but I actually know which patient IDs had those values. So then I could go back to the raw data or ask my researcher to double check and say, is this the appropriate value that was supposed to be entered? You can also use PROC Univariate to test for normality by adding the options normal and plot. The option normal gives actual tests for normality, and the plot statement provides the simple plots, the box plot, a histogram, and a stem and leaf plot. These aren't publication quality graphics in this example. We will look at examples later where we can produce publication quality graphics that check the distribution for normality. So let's see what happens when we include these options normal and plot. So here again we get the exact same output, starting with moments, basic statistical measures, tests for location. We are also now adding tests for normality. And I'm just going to focus on the Shapiro-Wilk test. So with the Shapiro-Wilk test with a p-value of 0.0064, it tells us that the variable BMI is not normally distributed. The null hypothesis for the Shapiro-Wilk test is that our distribution is normally distributed. With a highly significant p-value like 0.0064, we would conclude based on this test that our data is not normally distributed. But then if we scroll down, we also see some plots. We see our stem and leaf plot, we see the box plot, the little plus sign indicates the mean, and we have the normal probability plot. So if we looked at this plot, particularly the stem and leaf plot, we see that our data appears to be bimodal, or 2 humps. So PROC Univariate can be used for helping us gain a lot of insight into the distribution of our continuous variable. It provides even more detail than PROC means and can be very helpful when you're first looking at a data set, trying to understand the distribution of your variables, whether they're going to need transformation, whether there were data entry errors. It's a very helpful procedure for diagnosing problems in your data set among your continuous variables. This concludes the demonstration on simple descriptive statistics.